This conference will now be recorded.
Hi, everyone. Welcome to the TAP meeting number 36. This is probably the one before last for 2021 as we are wrapping, and we'll soon start with our main theme with Chris. But before that, some updates. So our TAP group is growing. The number of volunteers and the number of activities is it's just great to see the progress we're making and the involvement of everybody joining in. Just to highlight what I'm talking about, our TAP wiki page was updated with the latest work streams, with workstream number 1 and number 2, which we've been focusing on for developing OpenTime server and the PTP profile, have already made their first contributions. And then work streams 3 and 4 are in different stages of development for their specifications and time APIs and oscillator classification. The new streams are 5, 6, and 7, which were added this month, and we are at the stage where we are about to announce them. And we will be approaching you and your colleagues for participation and involvement. I think this will make the contributions, this will make the work meaningful and useful for the entire ecosystem. So I encourage you to spread the word. If the names and the means to communicate are available on the website, the names of our leaders, Alon, Anand, Julian, Gautam, and Yuliang, and please feel free to reach out to them on any question. Also, Ahmed and myself are here. So today's discussion is about the last inch. So having synchronization at the last inch. If you had attended the TAP Global Summit, the exhibition hall, you have met probably Chris and the rest of the folks and have seen already the demo, but now it's the demo time. I'll pass it on to Kevin for more context and introductions.
Thanks a lot. So my name is Kevin, and I'm not the main event, it's Chris, as was mentioned, but I just wanted to give a couple of introductory remarks as Chris gets his presentation up. So Chris has been involved, Chris and I both work at Intel, just FYI. So Chris has been involved in PT 1588 since I think 2006, something like that. He actually implemented one of the profiles, GPTBD. So he has some in-depth implementation experience with that particular profile. And a year ago, last month, I guess, I gave a talk on timing in the last inch, and it was a bit hypothetical. Chris is actually coming today with measurements. So you'll see some graphs, actual measurements, recent measurements. I think in the last week he collected these, the final data that he's going to be presenting. So talking about getting time into the application, software applications. So that's all I wanted to say. Chris, why don't you take it away? I think you're muted currently.
Okay. Yeah. So everyone can hear me and see the slides. Okay.
Yeah, looks good, Chris.
Yeah.
So today I'm going to talk about PTM measurements, platform clock offset measurements using PTM. So we'll get started. My name is Christopher Hall, and we'll get going here. So the agenda for today is I'm going to talk about the problem, why do we need PTM? And then we're going to have a short discussion of the PTM protocol, and so a little bit of detail around that. And then I'm going to talk about the test methodology and measurement results. And finally, we'll take a look at some next steps and call to action. So start with problem statement. So, as some background, we have it's relate. So PTM is closely related to PTP, synchronization within the platform rather than synchronization across the network. So, as by way of some background, the PTP protocol software enables synchronization of the network device clock with the GM. So what we have is that the GM, using the PTP protocol, we can replicate the GM clock on the network device itself. But there's a problem because that device clock is not, the network device clock is not readily available to software on the platform. So there's some problems with this. Issuing a read to the device requires read across the PCI Express bus or some internal bus, and this tends to be quite slow. Latency is going to be in the hundreds of nanoseconds. It varies greatly, but it's it's not as readily available. So for example, the system clock has much lower latency and sub 100 nanoseconds, at least on Intel platform. So the Linux PTP solution, and this is I'm going to sort of focus on Linux PTP here and how Linux PTP synchronizes within the platform. The Linux PTP solution uses PHC to sys to synchronize the system clock. And so the system clock is typically going to be based on the CPU timer on Intel platforms. This is TSC, timestamp counter. And so PHC to sys synchronizes the system clock, again, based on the CPU clock to the device clock. And by default, PHC to sys uses a software method to compute the offset between the clocks. And this introduces some inaccuracy, which we're going to take a look at. So this is an overview of how the offset is computed by PHC to sys using software. So it's really, we read the system time, read the device time, and then read the system time a second time. And the offset is the average of the system times minus the device clock time. And so the implicit assumption here is that the device time is sampled halfway between the two reads of the system time, which is not, it's the best assumption that we have, but it's not a correct one. So over the next few slides, I'm going to take a look at the PTM protocol and my test methodology. So here's an overview of the PTM protocol. So go ahead. Sorry.
The suggestions. I don't think you mentioned that PTM is part of PCI Express. Just a.
Yes. Okay. Yes. PTM is part of PCI Express, so it operates. I think that will become clear in the next couple of slides. But yeah, so it's a synchronization protocol that operates over the PCI Express bus. So this allows us to synchronize a clock on the host with the device clock located across the PCI Express bus. Great, and so we can actually we can jump to the. This
I wasn't trying to disrupt your flow.
Okay. But I'll modify the flow slightly here. I think this is the detail that we need here. So we have a PCI Express endpoint, and we have a clock in the root complex. And using PTM, we can measure the offset between the clock on the root complex versus the clock on the PCIe endpoint. So, and this goes some into Intel specific implementation. We have a platform clock. This is the ARC clock, and this provides time everywhere on the system, including the CPU. So we have a way of using PTM directly relating the device clock to the timestamp counter, as I previously mentioned, which is also used as a basis for excuse me, the Linux system clock. So then we can get a little more into the detail of how PTM works. So we have so the terminology is slightly confusing at first glance. So the upstream port belongs to the downstream device, which is the endpoint, and the downstream port belongs to the upstream port, which is either a PCI Express switch or the root complex. And so the downstream device makes PTM request, and the upstream device responds, and we end up with four timestamps. And using those 4 timestamps, from the downstream port, we get the propagation delay that's derived from T3 and T2, and so the downstream device, excuse me, uses the propagation delay as well as the two local timestamps to compute the offset between the device local clock and the upstream device clock. And that's the details of that are shown at the bottom of this slide. Okay, and so here's an overview of the test methodology. This is a much simplified diagram of the previous platform. So we have the ARC clock, which is the basis for time on the platform, and we can directly measure this using the time GPIO device. And again, ARC provides time to the root complex, which provides time to the endpoint device. In this case, the endpoint device is the I225 network interface card. And for all these tests that I've done are on Intel Atom platform. I have the complete product code on the slide. It's an Elkhart Lake platform.
Hey, Chris, I think I may have asked that before. Would that be the only system available today to showcase PTM, or you need some special code for that? How can our audience, right, be repeating or hopefully implementing PTM today?
I'll step in there, Chris. So it's a fair question. And this is an Atom processor. There's also a Core processor, Core i7 or whatever. Probably what we should do is follow up on that a lot, and we can provide some more details if people want to reach out to us directly. But yeah, these are commercially available platforms, at least the Core and the Atom. We can share more later.
Great, thank you.
Okay. All right. So over the next few slides, I'm going to take a look at some of the measurements that I've made. So first, we're going to take a look at the current state. This is without PTM, where we are measuring using the software offset. So I'm going to do this measurement on an idle system, and then we're going to load the system and do the same measurement again and look at the difference between those. And we'll do the same thing for using PTM as well. So here our measurements where we are not using PTM. This is the software offset, the details that I had on previous slides. So here we don't have any hardware support for cross time stamping. We're just simply computing the offset between the device clock and the system clock using these software reads of the time. So on an unloaded system, we're going to see we're going to see a pretty large bias. Actually, let me take a look here. So I think we should go into a little bit more detail here. So basically, the time GPIO produces a pulse per second output. The I225 produces a pulse per second output as well. And I measured this offset using a logic analyzer. And these and on these measurement slides, that offset is what I'm graphing here. So so on an unloaded system, we synchronize. So we synchronize the clock and then measure the offset between the time GPIO and the I225 clock. And so it's a little bit because of the scale, it's a little bit difficult to see the unloaded case, but the peak-to-peak jitter is about 38 nanoseconds, and we see a bias of about 500 nanoseconds. And these biases are something that I'll go into a little more detail, but the bias is something that the software is not able to sort of quote see. So PHC-to-sys does not see this bias. The 38 nanosecond peak-to-peak jitter that you can see in the software offsets used by PHC-to-sys, but this bias is not present there. And as we load the sys, go ahead. Sorry.
Yeah, sorry. 2 questions. I'm just curious to know what is the frequency of these PTM messages, and then second question, how does these results compare with PHC-to-sys, for instance, not running PTM?
So this slide is PHC-to-sys not running PTM. So I'm not. So to clarify,
yeah.
I'm using PHC-to-sys to synchronize the clocks.
Okay.
And then we're measuring the result of that synchronization. So this is PHC-to-sys synchronizing the clocks without PTM.
I'm sorry, just to close on this one. I think what Michelle meant is TS to PHC, which actually uses the PPS input on the NIC, for example. Do you have any, because it's a lot more precise even in normal circumstances than PHC-to-sys, so do you have any data on this one?
Yeah, I do. I do not have that data. I would argue that PTM that would accomplish the same accuracy, but that would be a good test to do. But so what I have are just the PTM and software offsets. But yeah, in the future, that would be something I could.
I guess the point here is that Chris, you didn't want to use any extra wires, so there are the only wires being used here are connecting the system to the logic analyzer, right?
I have a different question about the PPS generation from the always running timer. Is it done autonomously by the hardware detecting, like when a full second elapses, or is a kernel driver involved in the critical path? How does it happen in this measurement?
So I'm used, and I'm not. not sure this is the answer, but maybe close to the answer. But there is a kernel driver that's involved there, and so each of these pulses I'm scheduling separately using the time GPIO hardware. That's the answer to the question.
So you arm the GPIO separately for every second. That's fine, but it's the hardware that detects the second has elapsed and raises the PPS out. It's not software raising the PPS out manually.
Yeah. So I think your question is so the time GPIO does have a deadline, and it produces an edge on that deadline. So it's timed. So there isn't any involvement where the software triggers the output. That the output is triggered by the out timer.
Yes.
That's the question. Okay.
Software schedules the edge, hardware executes the schedule.
Thank you.
Okay. And so I think to continue, so when we've loaded the system, again, without using PTM time synchronization, the bias becomes much larger, and the peak-to-peak jitter also becomes much larger. So now we'll take a look at the case where we're using PTM, and the scale of the graph is much smaller here. On the previous graph, it's plus or minus 2.5 microseconds. Now we're at plus or minus 10 nanoseconds. And so we have, again, the exact same loading as the previous graph. And there's no, so these are two runs, and I've graphed them on the same graph just to contrast. And the peak-to-peak jitter is exactly the same for the loaded case versus the unloaded case. We do see a small bias here of 2 nanoseconds, but again, the accuracy of our logic analyzer is in the range of about 2 nanoseconds. So I'm not sure that the bias is actually there, but the main takeaway here is the peak-to-peak jitter is small, much smaller than even the best case of software, and excuse me, and its peak-to-peak jitter is insensitive to the system load.
May I ask what the load was? What do you mean by loaded system?
Yeah, I have the same question.
Yeah, so I'm loading the system with a lot of bus locking. So this seems to produce a large amount of jitter on the MMIO reads and writes.
And I think Chris, so as a next step, has a recommendation that we define some. Yeah, I think you're Chris on this one. You're looking for what is a quick and dirty, really terrible interference that you can really demonstrate a large difference, and then we can look in the future at what's realistic. But this should be this is pretty bad, right?
Yeah.
As you can see from the previous slide.
Yeah, I can't imagine that it probably gets much worse than this in terms of the jitter. So some of the measurement takeaways, which I've already probably gone through most of these, but the software method of offset computation introduces an unknown bias. So PhD desist again is not going to see this bias. If you look at the output of PhD desist, this 500 nanoseconds or up to 1 microsecond of jitter is not going to you're not going to see it there, and and this bias also varies based on system load. There isn't really any way that the system could be benchmarked and subtracted out, for example. And in the best case, the offset jitter is going to be more than double that PTM. So PTM offers, and in contrast, PTM offers a solution that does not introduce bias, has much lower jitter, and is almost completely insensitive to system load. So, and some practicality here of how do we actually use PTM to improve application performance. PTM requires support in the endpoint device and root port. Linux, so by default, Linux enables PTM support. The OS does enumeration of the PTM protocol capabilities, and so that by default is enabled in Linux. And there's driver support required also. So I'm not going to go into detail of how these cross timestamps get up through the stack, but the driver needs to make these available to the Linux PHC interface. And Linux PTP, this is PHC assist, by default will use the PTM timestamps if they're available. And so probably a few years ago, I did some work in the Linux kernel, and so there's an additional IOPTL for retrieving hardware cross timestamp. This is PTP sys offset precise, and this Linux PTP prefers prioritizes this method of cross timestamping when it's available. Okay, and so for next steps and also a call to action. So I'm going to repeat. So future work is to repeat this using other loads, potentially more realistic loads, hopefully, and validate also for longer runs. These are relatively short runs of 1 to 2 minutes. And so a larger call to action for the group is that we should adopt a methodology for measuring synchronization within the platform and agree on standard CPU or /IO load for measurements.
I have another question.
Sure.
In this, PTM has a very rigid clock hierarchy, enforces a very rigid clock hierarchy essentially. So in this case, the root port is effectively like a boundary clock for the system. If you have multiple NIC cards in your system that are connected to the root port, and one of them has the source of time, then you have to synchronize the root port, and then all the other devices that want to have this time synchronize to the root port. They cannot synchronize to the NIC with the most precise time from the grandmaster. What do you think the effect of that might be by putting the root port in the middle, and how far it can scale to how many devices? Do you see any problems with that kind of architecture?
If I could make an initial comment, Chris, I'd say it's exactly the same as what we have in the network, actually, because we have a GM, but of course, applications do things based on that time, and it's just a shared time. So I think of the PTM time as a shared notion of time that can be used to pass anyone's time to anyone else. In fact, you could have an arbitrary number of different clock domains being passed using this cross timestamping. In this case, we're moving time to the system time, and then it could go back to the other devices through PHC assist, or the raw PTM time could actually be used as a reference to map or port clocks from one device to the other. And I think there's, yeah, I don't see a limitation in terms of scalability. I think switches are supported.
I think that's the key. That the PTM clock provides a reference, and there's quite a bit of flexibility in terms of how clocks are propagated from one device to another.
And when we first defined this protocol, there was some discussion in the PCI group, PCI SIG, about having a BMCA, but then we have to add domain numbers and all of that. And we decided, let's just have a single clock reference, just like we have a single TSC, but you can have all kinds of POSIX clocks that are based on that. So this was the solution that we came to. But it's a great question, though.
Okay. Are there any other questions?
I think, Chris, also you maybe didn't make as big a splash as as you could have. I mean, you know, to go from, you know, thousands of nanoseconds, worst case of error, down to, you know, plus or minus, you know, 15 nanoseconds. I think that's it's pretty amazing improvement, actually. It's like going from NTP to PTP in some ways.
I have a question.
Sure.
My impression or my hope was that PTM can help us to measure single one-way delay. But if I understood correctly how PTM works, it is actually measuring two-way delay and dividing by half, assuming that the path between the devices is symmetrical. Is that correct?
Yeah, that's correct.
Yeah, and Chris, I think you had that equation, but I think that equation did not apply to PTM. The previous slide. Where you divide by two. Previous, go back to.
I mean this slide.
Okay, here was also divided.
I'm talking about the next slide. This is not about PTM. I understand this, but this is PTM, correct?
Yes, yes.
So when we are under load, how can we guarantee that this path is symmetrical?
But this is a single trace on the board.
So there is no sending messages between devices?
This is a PCIe device plugged into a root port.
Can you return back the slide? I see something. Yeah, this one. Thank you.
Sorry about that.
So we know for sure that there is no, if there is a delay, it is happening on both directions.
But yeah, and it's speed of light over the FR4, FR5.
This represents a yeah, this is more or less a wire. So the PTM response that the T3 minus T2, that would be the only sort of variable piece here, and this is something that's taken care of by the timestamp on the upstream device.
Okay. So in some sense, it behaves as a transparent clock here. Okay.
Yeah, and I guess the point is that this is like looking at the Ethernet Cat5 from one switch to the other, where we assume that the delay is relatively fixed and symmetrical. It's exactly the same assumption here over between the pins of the NIC down across the connector, across the board, and to the pins of the SoC.
Okay, looks good. And my next question is about the command that was mentioned in the site in one of the slides, where we measure, we gather a number of samples, and that's how we look at the offset between the system clock and the PHC. I have some experience. I think it was a few more slides.
Okay.
Forward, please. Yeah, this one. Sys offset precise.
Okay. Sure.
So my experience with this is not very positive. maybe something was missing on the hardware or on the machine, but I've seen a variety of answers coming back. What do we need to check to make sure that this sys offset precise actually can give me the best answer that I can get?
Okay. Well, so which I mean, it's a little bit hardware dependent. I mean, certain more driver dependent, but yeah, I guess without knowing the specifics of the hardware. So I mean, this should be used only to implement hardware cross time stamping.
But even then, if you look at the if you look at the PTP4L code, and I think I look at Cronny, there is a process of getting the outliers. I mean, removing the outliers, and there is also filtering happening on top of it. So
yes.
Yeah.
So the way PHC assist works, there isn't any. With software cross timestamps, there is some. I think it's by default maybe reads this. So it'd be let's just look. So this is done maybe 25 times, I think, for each read. So I think there was also a question of how many times per second the PTM is running. So it's eight times a second. And similarly, if we were going to do this I did do this cross timestamp eight times a second as well. And typically this is done several times, rejecting the largest outliers, which are determined by the the difference between S start and S end. So PHC assist will select the I think it's the smallest one. I think it just selects the smallest one. I'm not 100% certain on that. So yeah, I mean this will reject that, and then there's the filtering stage as well. So the filtering stage is the same regardless of whether we're using hardware cross timestamps or software cross timestamps.
Yeah, and I just to add that the graphs that Chris is showing here, we're looking at kind of ground truth raw measurements. Yeah. And of course, you can average, you can remove outliers. There are a lot of things that you can do above that. But remember, you're paying quite a heavy penalty in all of those MMIO reads as well. Those are not free. And so yes, this is not what you'll actually get in practice. There are ways of mitigating this. I think what Chris wanted to show was that if you just go down and eliminate all of that filtering and other intelligence and outliers and so on, and just look at the raw data, you can get a pretty compelling improvement in the end-to-end accuracy with a reduction in system load in terms of the MMIO reads.
But if I understand this correctly, if everything is properly set and I have the right hardware, I'll get the offset in the range of single-digit nanoseconds when I go through this API. Is that what I should expect?
Yes, that's what you should expect. I mean, if the device is really using hardware, so we're talking about the PTP sys offset precise.
Yes.
That should be that should reflect a hardware offset. And if it does not, then I mean, most likely it's a driver problem, but because so there's sort of three sort of methods. There's the old methods where the PTM, the PHC stack reads directly, reads cross timestamp and then just directly reads the device time. There's another which is actually what I use, the extended, where this functionality is pushed down into the driver, and the driver it's still in software, but it's a cross timestamp in the driver. And now we have PTP sys offset precise should be used only where the hardware itself is where the cross timestamp is in hardware. I think that's the that's kind of the purpose of Linux PTP prioritizing that over the other methods. So it should reflect the best cross timestamp that is available for hardware.
Okay, thank you.
One question, could you, for instance, explain maybe the sources of errors that could eventually contribute to performance degradation? Like what you've shown is really, really good, but what exists in the system that could lead to performance degradation?
The timing synchronization performance, Michel?
Yes,
in terms of, so what would take us from, just to clarify, what would take us from the red line to the, well, I mean, the red line is I get, yeah. So maybe from the red line to the green line, is that kind of the question?
Yeah, when you have PTM enabled, like you've shown really good results, you know, nanosecond level, but are there sources of errors that exist within that system? And I'm not familiar with PTM that could lead to performance degradation, or something happening at the IO level, or maybe traffic in one direction versus another one that could lead to you know, some level of degradation. Thank you.
So I think the so this is kind of at a high level. Go ahead.
I think he's saying, if I have PTM, is there something that can make those numbers bad? I think the answer is shouldn't be. I guess maybe I misunderstood the question. In PTM there should be nothing that would make these numbers bad. The only inaccuracy it would have to be some sort of hardware implementation problems. Yeah, Michel, the point is that we're relying on the speed of light, propagation of the electric wavefront on the traces to be, you know, symmetrical and constant. And then there's timestamping in the hardware of these PTM messages, just like if you have perfect implementation of transparent clocks, or, you know, from a point-to-point perspective on an Ethernet link. PTM is effectively PTP implemented in hardware and state machines between the two link partners on a PCI Express link. If there's a switch, then the switch actually, Chris doesn't show this, but the switch acts like a transparent clock and adjusts the residence time in the protocol. So the PCIe switches will act like a transparent clock and introduce the correction field.
Hi, this is Alon from Kisa Technologies. So at a high level, and please correct me if I'm misstating anything here, Chris, but typically the limitation of the accuracy on PTM is number one, the resolution of the timers on both the timer, you know, your root a complex timer, as well as the resolution that you have at your endpoint. So you're never going to be better than those. Plus, there is you're going to end up with a plus minus one in each on each side, because there is so in each case you're going to be, you could be off by plus minus one count. And the same thing happens when you go through a PCIe bridge. Is again, while there is a correction, the correction could be again off by, you know, plus minus one measurement clock cycle.
All the standard stuff.
Yeah. So there is going to be so there is some amount, so beyond just the, you know, the speed of light, there are some, you know, physical limitations, but this is, at least in theory, addressing all other inaccuracies, at least over PCIe.
Yeah, standard stuff.
Right.
Hey, Chris, I have a quick question kind of related to Intel architectures. For a server system where there's a PCH attached to the CPU, is the PCH acting like a transparent clock, like in your diagram, or does it have to do like PTM between the PCH and the downstream and then CPU to PCH?
Yeah, and I'll just jump in here, Chris. So if you look at a core system, those have you know, a south PCH and a north CPU die. Yeah, so that's just handled. You know, don't want to get into the microarchitecture, but the point is that there's this common ART timer, and that is basically the PTM clock, as well as derived. The TSC is also derived directly from it. So those are dealt with within the microarchitecture.
Okay, got it. Thanks.
Other questions for Chris?
Well, one question with regards to, let's say, the TSC, a little bit more in details. So there's the PLL is like a digital PLL, I'm assuming. Like the implementation is like you're basically accumulating some values, and then that like the steering happens basically by that number that you're adding, the accumulation. Is that correct?
Yeah, November last year. I'll just jump in, Chris, on November last year. My presentation actually walked through the derivation of the TSC based on the ART, as well as ART being used. So it was you know, theoretical, but I have yes, basically the TSC equals ART times the integer divided by a power of 2 and adding a constant, and that's just the architectural guarantee from the SDM.
Yeah, and a little bit of detail. The PHC desys can be operated in either direction. It can either synchronize the endpoint to the system clock, or vice versa. We're doing it system clock to the PCI endpoint, so there isn't any change to those parameters in the system clock. So the system clock, I guess, is running at its default kind of configuration, and we're not changing that. So, for example, adjust time X not being used, we're only making adjustments to the network clock.
And like with regards to the CPU itself, like can this CPU use the TSC to timestamp events? Let's say, for example, in the assembler level, if I have, let's say, one instruction, I can get the CPU to give me a timestamp from when
it's
that instruction.
It's instruction RDTSC. Read the TSC.
Awesome.
And there's a TSC deadline timer as well. So we can
awesome.
So that's tied into the HR timer.
And then we have one TSC for the entire multi-core, or you have like per core one?
They're all synchronized.
Okay, so it's like one that is ghosted. Is it like something like that?
If you, they are synchronized. If you read them, time will never go back. The requirements in that sense is that TSC must never go backwards, even on a multi-core system, so long as you're cache coherent.
Yes. Okay. Thank you.
Otherwise, bad things happen, especially on certain operating systems. Hey, Chris, let me go a little deeper on one question someone had asked earlier, and I know we've discussed this for years, but what you're showing here is synchronizing between the device clock and the system clock, the POSIX time, let's say. But as someone mentioned, if I have two PCIe endpoints and I'm, let's say, implementing a transparent clock or a boundary clock, I'd like to be able to have those PCIe endpoints share a time. So I'd want to discipline one of their device clocks with and have it match the device clock of another PCIe endpoint. And there could be some benefit if you use the ART, the PTM time directly, rather than mapping it up to the system time, right? Any thoughts on that? I know you've looked at that.
Yeah. So, well, I mean, so there's sort of maybe two levels to look at that. Even where we transit the system clock, that's currently not supported in PHC to sys. So that's I mean, I think that there might be other solutions to that, but using the hardware cross timestamp, we don't currently do that. So that's sort of one level of where we need to add some functionality there.
Right.
But then, yeah, then there would also be using the cross timestamp at maybe the art layer, and so there's been some I think so this is a cross timestamp API. And I think that's where we would want to be going with that, where we have a cross timestamp API where I say, here are two. So we have like sort of clock get time, and there's several clock set time, for example, and there's a clock ID. So I think eventually where we want to go, would have a clock get relation, something like that. Where we provide two clock IDs, and it will get, and now underneath, the Linux kernel does whatever is appropriate to relate those clocks, and that would give us an opportunity to use art for that. And it's the idea of sort of maybe exposing art directly is probably not something that would be a place to go in the Linux kernel, but we could introduce this new API.
If there's a lull, maybe Chris, go to your next steps too, and let's see if there are any of the work streams would like to pick up those calls to action.
Yeah. Okay. Yeah, and so I think the calls to action are these last two bullet points here. So you know, I think I've proposed a methodology here for measuring using hardware output to measure the offset, and so that would be we maybe settle on a methodology for measuring that, and then also another call to action where we agree on the standard CPU I/O load to determine. So we talked about the loading. Let's standardize on loading to for future measurements.
Is there a work stream, guys, that would be appropriate to pick up or consider these?
So this is Alon. So we're starting a work stream on the servo behavior to define, and I think this would be a good subject for that work stream, but I'm saying that, of course, because I'm driving that workflow.
I tend to agree, Alon. I mean, I think it can find a nice home over there. It's kind of intuitive, and if it doesn't make sense, we can, of course, discuss offline with Intel.
You know, Elad, Anand Ram here. You know, we're starting a measurement and instrumentation group, which you think this would slot straight into. So I almost think Kevin was giving me a lead in. I do think that I agree with Alon. This is, you know, the group that we're looking at will focus, I think, initially on measurements, of course, but probably look at measurements to the, you know, tens, hundreds of nanoseconds granularity and accuracy, those applications where you're measuring across systems or even entire data centers, whereas this is a, you know, board or component level measurement. And while it is a measurement, I think Alon's right, it does fit in with a lot of what Alon's going to be doing does need to involve measurement as well.
I'd like to return a little bit back on the question about TSC, because we had multiple discussions in the past. And this is the first time that I feel that we are close to have an answer. First, what Ahmad asked about different TSCs on different cores, and you said they're synchronized. But there's another question about how the power level affects the TSC accuracy. And is there anything that we should expect based on how the CPU power level is?
Yeah, there are CPU ID leaf bits capabilities. There's in TSC time invariant. There are several bits that indicate the trustworthiness, let's say, of the TSC, because there have been problems in the past, but modern day CPUs that I'm aware of, yeah, even like core, your laptop in front of you, if you have a 4-core, 8-core processor, those are going to sleep all the time, but yet the TSCs continue to be synchronized. If not, Windows will blue screen and Linux will choose another clock source.
I would love to expose some of these bits to the API level. I think it's important on the software side to have more visibility, how the system behaves. And the next question would be how stable is the TSC? If I don't go on discipline the TSC for a certain period of time, what is the maximum error I should expect?
Yeah, and that really depends on what the XO is on the board, and it's typically an XO. It can be in some cases a much more stable oscillator, but yeah, it's a 25 megahertz crystal typically in servers, 19.2, 38.4 is coming in. So it's some tens of megahertz crystal that's drives everything inside of the compute and I/O complexes, and it is the source of ART. ART actually ticks one time every time that crystal ticks.
Just quick to clarify also, Kevin, is the CPU like this speed stepping, like, I don't know, it's for energy saving, whatever, like, does that makes any effect on this or not?
Yeah, and maybe I should do a refresher because it has been a year since I went through that, but the TSC equals that crystal clock times a constant divided by a power of 2 plus another constant, basically, that only the change. So it really is a locked directly to the crystal driving the platform.
Thank you.
Do I have access to this constant?
Yes, it's in CPU ID leaf 15 hex.
I remember there was a lot of discussions about exposing this on the Linux side, and if you look at the source code, there are some comments there that says there's some history behind this, I guess.
Yes. Yes.
I think we have one question left. When do we get server-grade platforms with PTM support?
Yeah, great question. We can address that another time. But I just, if I could, for the last word here, I want to really thank Chris for digging in, and these numbers have been a lot of work and many years in coming, and I think it's going to improve our ability to trust time and use it in a reliable way in that last inch between the network interface and application software. So really big thanks, Chris, for this work.
I am joining that. Thanks, Chris, and thanks for all the efforts demonstrating that to us.
Yeah, thank you, Chris.
Okay, if no further questions, we will close off this call, and we stay tuned for the next one.
Thank you.
Thank you.
Thanks, everybody. Thanks, Chris.